Okie doke, we're going to do a little bit of word association to wake everybody up after the break. So, shout out, what do you associate with this? All right. Anything else? This perhaps? Well, I'm going to show you next what the Interwebs told me, what it thinks of Manning. So what was that result? How did we get there? To explain what happened, first I need to explain what we're actually doing. So what are we actually doing? We're mining web pages. Which web pages? All the web pages for insights. How are we doing it? We're using machine learning to do the heavy lifting for us. We're using classifiers to filter or bucket the data. We build topic models to try and discover concepts related to words. That's roughly what we're doing. How do we do these things? Well, first of all, we need data. So I'm going to cover briefly, going to talk about getting data, manipulating data, and then using data science to get to this fascinating discovery of what the interwebs think of Manning. So under getting data, I'm going to touch on DMOZ and the common crawl. Under manipulating data, I'm going to talk about Spark and sparkling, the bindings for Spark, and RDDs and data frames. And under data science, after a whirlwind introduction, I'm going to talk a little bit about MLlib, which is Spark's machine learning library, classification, random forests, and LDA, which is latent Dirichlet allocation, which is a form of topic modeling. So first off, getting data. How do we get data? Where does it come from? We use DMOZ. Which is the Mozilla's directory. It came out of the Open Directory project. It claims to be the largest human-edited directory of the web. It's pretty useful when you think about it in terms of free, crowdsourced, labeled data. Like all things Mozilla, it's kind of a dinosaur, though. And as with all crowdsourced things, there's a bit of a double-edged sword. We can't be entirely sure how accurate the findings are. But briefly, a DMOZ page will have a topic like fashion magazines or news or whatever, and it'll have a bunch of links things under that topic. So we use that as pre-labeled data. Commoncrawl.org is an open directory of web crawl data that can be accessed and analyzed by anyone for free. It's hosted by Amazon. The data is freely available. At this point, they do monthly crawls. They've been doing that for about 2 years now. They have readily accessible index, so you can look up sites and basically fetch the data for those sites or pages. It's actually on a page-by-page basis that they've fetched. And there's tons of data. They have the raw HTML with HTTP headers. They have a couple cooked forms that includes links and metadata. They have just a stripped plain text. Quite a great project. Lots of data there. If you've ever done web crawling, it's actually really nice to have something where you know you can reliably just get this. You're not dealing with redirects. You're not dealing with all the various forms of HTTP goodness that's out there in the world. So how do we use these two things together? We use DMOZ to sample positive and negative seed sites. So in my case, I'm looking for fashion websites. So if we end up with an example like Vogue.com or Elle.com, we can look that up in the Common Crawls index, and we can find all the pages that are part of Vogue.com or Elle.com, and this kind of explodes our data set. And then with the information that's in that index, we can basically just pull down from Amazon the format of the data that we're looking for very easily. You can fetch all your data and then very little fuss, and basically, we started with looking for fashion sites. We scraped DMOZ. We got like 900 links. or sites that we thought, okay, that's maybe not very many pages. But as soon as we looked them up and deduped them in the Common Crawl Index, we ended up with about 2.5 million pages. That's a fair few documents. And then similarly, we picked non-fashion examples of news and sports and whatnot. There was more than enough. Again, put it through the index, pumped out 8 million documents, no problem. So then you can balance to taste. So now that we have a load of data, more than we expected, how are we going to use it? We need to be able to manipulate it in a scalable way. For this, we used the Apache Spark project. Spark is arguably the next big thing, or even the current big thing. IBM are pretty much all in with Apache Spark. I was at a Spark conference there recently. It is the big thing at the moment. I think IBM have 3,000 developers they're putting onto it. So it's here to stay for a while. IBM alone have invested so much in it, I don't think it's going anywhere. It's quite a good project, in fairness. Like there's warts, we'll go over some of them, but it's pretty good. Sparkling is the Clojure bindings to Spark. It's one of the Clojure bindings to Spark. There's a great presentation on Spark and Sparkling. I highly recommend you look at it. He covers, Dr. Christian Betts, who wrote it, covers Spark and Sparkling in the introduction way better than I can. So I would definitely give that a look. At its core, Spark has two main data structures or ways of manipulating the data. RDDs, which stands for Resilient Distributed Data Sets, and data frames. RDDs. These are very familiar to, they're actually very familiar to Clojure programmers because they basically look like sequences. You use map and filter operations. Mapcat becomes flat map. But essentially, you can think of them as a distributed, sharded sequence that you can operate on. There's a number of partitions, or a number of executors that each have partitions or shards, and they operate on these sequences, and you work on them in a very familiar way. Spark kind of differentiates between what it calls transformations, which are things like map, filter, so on and so forth. And these are lazy. These are something that will be done once you call an operation on it, which is something like count or reduce or whatever. And then the kind of chain of computations gets collected and run. Again, for most Clojure programmers, this is all pretty familiar. So to give you a brief demonstration, I'm going to give you everybody's favorite machine learning tutorial. Okay, let's do a different tutorial. I'm not going to spend a lot of time on this slide because the next slide is very similar. This is what code looks like in Clojure, just with the reducer library to compute some prime numbers, or to sieve out some prime numbers to be more accurate. This is the Spark code. You can see that the shape is very similar between the two. Map, filter, remove, subtract, stuff like that. So going over this one briefly. So this, up on my GitHub, there's a project called Sparktimus Prime that has both of these examples and the full code around it to run it. But this is the core function where you give it the primes that you're interested in sieving out. The numbers RDD is all the numbers that need to be sieved have multiples of primes sieved out of it. So pretty much we want to know which is the highest number prime, how high we need to count up to. And then we create an RDD using the parallelize operation. This basically creates a sequence that's distributed. The context is the Spark context that's passed in, and we give it the prime numbers that we want to parallelize over. Then basically, flat map is the same as mapcat. And basically, we generate the multiples and filter them out. So our candidates then, we subtract out of the numbers we have the prime multiples that we've seen. We cache that because, because in Spark, when you create one of these operations on it, if you don't cache it, it'll do it again if you reference it again. So you just need to be a little bit aware of caching results or not. So in a lot of code, you'll see cache and unpersist kind of littered throughout. But basically, if you're using the results of an RDD more than once, you probably want to cache it. So then our new primes RDD is we take the candidates, we filter out all the ones up to the one we needed, and we cache that. And then the rest is pretty much returning results. We get our new primes. Collect is give me the results, sort them, put them into a vector. Remaining RDD is we subtract out the ones from the subtract out the new primes from the candidates. Unpersist is the opposite of cache. It says we're done with this, and then we return it. So that's RDDs in a nutshell. I'm going to talk a little bit about data frames, but before I do, I'm briefly going to go on a little tangent. Those who cannot remember the past are condemned to repeat it. I remember 15 years ago, everything was MySQL, Oracle, SQL Server, blah, 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 LAMP stack, this stack, that stack. Oh, if you're not using stored procedures and the new fanciness and the great things, you're doing it wrong. Then 7 or so years ago, oh my God, you're using an RDBMS? What's wrong with you? You can't possibly scale. That'll never work. You're doing it wrong. Now it's come full circle back to Spark SQL, Google's Formula F1, where they said, actually, most application writers aren't smart enough to deal with eventual consistency, so we're going to write a layer that lets us just use RDBMSs again, because, you know, if you're using eventual consistency, you're going to get it wrong. So I don't really know what I think about this. It's kind of, I don't know, it's just the way it is, but I thought it's worth pointing out. Right, data frames are the other main way of interoperating with data in Spark. You can think of data, so data frames are inspired by kind of this in Python or actual data frames in R. It's tables, it's rectangles. We're back to rectangles. Data frames are the new hotness. It's how Python and R can achieve similar speeds with some of the new benchmarks coming out. Underneath the hood, there's something called the Catalyst engine, which is an execution planner. It's like a MySQL or SQL Server's execution planner. Because it knows what everything is, it can say, oh, there's a join there, but I can do a filter and I can optimize this and I can do that. And underneath the hood, it generates Scala source code, and then it uses heavy use of Scala macros, and it can decide whether to unbox or skip boxing and doing all these things to basically generate optimized execution plans of your data. And, oh, I only need to read these columns and these columns to do that, and so on and so forth. So all the mind share at the moment and going forward is in data frames and the forthcoming data sets, which is even more strong typing for the Scala heads. Spark is written in Scala, by the way, so that's why I mentioned that. Data frames are great in Scala. You know, it looks very natural. They use a lot of Scala magic, like implicits and whatnot. So some of the crazy things they're doing, you don't even notice. You just write Scala and it's there and it works and it's fine. From an interop point of view, it's not always that much fun. I've spent a lot of time with Java P and unpacked jar files to figure out what is actually happening underneath the hood. Working with data frames from Clojure, it's not always that pleasant. Scala folks really like their static declared types, and it's going to get worse with the data sets, which lets you put your beans and your classes, your very type-safe classes into data frames and do much more magic type-safe stuff, array type-safe stuff. So here's a brief example. This is basically creating a single column data frame. I've used this as a utility method when I just need to sub-select from something for whatever reason. You'll see that I basically need to declare the types of the thing, even though it's just a type, it's the integer type. Then I need to create a schema for it. So then given a SQL context and a table name to create for it, and features is the actual numbers I want to shove into this data frame. I create an RDD where I parallelize the features. I then basically have to create a row from the features, and then from that row, or from that RDD of rows, create a data frame with the features and the schema, then register it as a temp table, and then return it. So some of this verbosity can get a little bit tedious. At the moment, I'm not really aware of any libraries that are trying to help this out. Sparkling itself doesn't have a lot of the SQL or the data frames interop code. I know there's another project called Flambeau, which does have some of the interop code. There's definitely room to make some of this nice. I think there's probably, you could do some interesting things with prismatic schema or whatever to ease this burden, and it's something I'd like to look into when I have a little bit more time. I'm also just going to show you another couple examples of irritation. The .select function here in particular in that second line. Here I'm just giving it a name, but because of the vararg stuff that most Scala people don't worry about because the compiler deals with it, here you have to give it a word and then you have to give it a string and then an array of strings. Whereas in other cases, if you're giving it column objects, you have to give it a column, or you have to give it an array of column objects, blah, 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 blah. Similarly, once you have a row, it's all the irritation of give me the string, give me the int, give me the thing, you're kind of reverse mapping the schema back into a row just to try to do something with it. This is a similar example where, see, we have the .call where it's actually a column object. And you can see we're selecting multiple column objects, but here we're creating an array first and passing it the whole array. And this is all to deal with variadic arguments and compilers and stuff. It's not all that much fun. But having said all that, and this applies to everything I say in the talk, there are warts, but it can do an awful lot of useful things. So we put up with them and we try to make them better where we can. So I'm going to give you the machine learning elevator pitch for those who don't know much about machine learning. The key points on machine learning. It's basically using statistical methods on large amounts of data to hopefully gain some form of insight on something. Generally, you use vectors of numbers extracted by you from your data. These are usually called feature vectors or features. Classification is a very broad form of machine learning that involves putting things into buckets, i.e. fashion-related website versus non-fashion-related website, in my case. Topic modeling. It's a way of finding patterns in a bunch of documents. Bunches of documents are usually referred to as your document corpus or even just a corpus. This is the 30-second pitch of what you need to know. So MLlib. MLlib comes with Spark. It's Spark's machine learning library. It's full of fairly cutting-edge, parallelized algorithms and utilities for doing machine learning at scale. Its goal is to make practical machine learning scalable and easy. It achieves this to a greater or lesser degree. Sometimes it's always parallelized, it's not always scalable, and it's not always clear why. And some things that seem easy aren't. There's two main packages. There's spark.mllib, which is the one that's been around for ages, and that's the one that's built on top of RDDs. And there's also spark.ml, which is built on top of data frames, and they have this idea of data pipelines where they're kind of making things look much more uniform in terms of, you can think of it as a protocol for, there's really only 3 or 4 different things you do with your data, so they're trying to make it easy to do pipelines, with this kind of setup. I'm not going to spend any time talking about pipelines because everything I had done to date had been in RDDs. But if you're starting, I would recommend starting with spark.ml if you can, because that's where all the new hotness is, and that's where all the query optimization and everything can happen. MLlib contains all the basics: vectors, sparse vectors, matrices, sparse matrices, dense matrices, labeled points, so on and so forth. It has stuff on feature reduction, and it has a ton of stuff that's really, really good and worth looking at. It has a good variety of algorithms. They're all designed to run in parallel. The guy in charge of the accepting patches for MLlib, I think, is known to, try to make sure that things are properly implemented before accepting them into the core. It's all really well documented, which is always a bonus. And there's a large and growing community. When I had problems, I was able to find answers pretty quickly, even if it was just don't do that. Not always, but it's a good community, and what's there is well documented. So one of the things is that MLlib gives us this, and this is what it aspires to. It wants to make machine learning Lego-like, that you have your blocks and you kind of push them together and you get results. Unfortunately, the reality of data science is that we often want this. We want to build complicated things, but we often need to dig into the nuts and bolts of things. We need to understand what's happening. We need access to what's going on under the hood. One example would be metrics. So binary classification metrics, it's a class for giving you metrics on your binary classifier. I'll talk about classifiers in a little bit, so don't worry too much about this if you don't know the terminology. But basically, it has some information you want, so you give it your RDD, it computes some things, fantastic. Unfortunately, you have to give your RDD to the multi-class metrics to get some of the more common, more useful numbers that you're looking for. And then neither of them actually give you the counts of the items by label. One of them, usefully or otherwise, will log it for you at info level, but it won't give you access to it programmatically. So if you need those counts yourself programmatically, you have to count it yourself again. So you end up iterating your data 3 or 4 times possibly just to get the metrics you want. Here's the metrics function I've been using. The RDD is the RDD of labeled points, and the model is my trained classification model. So you can see, basically, we take the RDD and we map it into a tuple of the prediction and the actual label. We cache it because we're going to be using it multiple times. We create the multi-class metrics. We create the binary classification metrics, and R is just the result I'm trying to return. I haven't put in all the metrics that I want, just because there's not room on the slide. But for example, F measure I get from the multi-class metrics, but the area under the precision recall curve I get from metrics. And then to get the actual label counts, like I said, I have to take the RDD and count it myself. Then at the very end, once you're done with it, you stop caching it because it takes up space until you tell it not to. Sometimes I think they're so focused, they've got their eye on the prize of, oh, we've got this algorithm, we've got that algorithm, isn't this fantastic? And we have these building blocks and we make it easy. Again, they're just missing, sometimes they just miss the mark a little bit. Another example would be the hashing term frequency. They use this in their examples for TF-IDF. They say, use this and it makes everything great and it's so easy. But when you look at it, you can't get back to the words. you won't be able to figure out what the numbers that came out of it map back to if you're actually trying to examine your topics later. And underneath the hoods, yes, they use hashing. Do they use a hash map? No. They allocate like a 2 gigabyte array of things and hash into it with a lot of collisions and a lot of wasted space for no real reason. So some of those things, once you see them, you end up rolling your own. For example of, I don't even know how to say it. It's just the functionality is all there. So there's something called a chi-square test where you want to choose just a certain number of features. The chi-square selector is great. You tell it how many features you want. It uses chi-square algorithm to compute them for you and give them back. But what if you don't know what the number is? You obviously want to be able to look at the results and then make a decision. Unfortunately, have to end up grubbing around in the source code unless you know the libraries very well, and find out that it uses something called it uses a Scala object called statistics, and it uses the chi-square test from that. So here's an example in code of how you would actually compute the chi-square test to get your feature, to figure out your feature count. So we create our labels and features data frame. We basically load some of our features from Parquet. Parquet is just a data serialization format, but it's columnar rather than row-based. So it's one of the things that makes data frames quite efficient. We get our labeled points. We get our bag of words. I'm going to talk about our bag of words in a few slides. So a lot of the first good few lines of that are actually just loading the data up. And then finally, we compute the chi-square. We get an array back from the chi-square test from our labeled points. And then in this example, I just log it to figure out what is it, what's there. In case you're curious, it gives you p-values and the statistics and the degrees of freedom and all the stuff from the actual chi-square test in statistics. And then you can use that array to make a decision on how many of these features you actually want to keep. So after all those, some of the warts in MLlib, like I said, it is still very useful. So we used it for classification with random forests. Classification, briefly, is using lots of data to tell things apart. We can put stuff into 2 buckets, or classes, as they're generally referred to, which is called a binary classifier. Or you can put it into many buckets, in which case it's called a multi-class classifier. There's lots of different techniques, random forests, logistic regression, linear regression, support vector machines. There's a wealth of stuff. A lot of it's supported by MLlib. It's what's called a supervised learning technique, which means that for each data point you have, you need to know what it is. So you need a label for it. So to tie this back into DMOZ, the reason we start with DMOZ is because we have a label for the data. We know that this website is fashion related or is sports related, or whatever your domain is, you can kind of decide and get a pre-labeled data set. So yeah, each thing needs a label and it has the features. Basically, it'll depend on what your domain is. In our case, the features are the bag of words. I've managed to make it this far without having to use the word count myself. We started with very basic word cleansing, just lowercase stuff, removed punctuation, basically removed anything that wasn't a letter or a digit, said it has to be 3 characters in length. Just drop anything that's purely numbers. When you're doing data science with text, word count is it's hugely important, so you can't avoid it. The bag of words and things you do with the bag of words, it sounds really boring at first, but you spend a lot of time on it. So the first time we were trying to create our bag of words, we ended up with way too many words. Like even on a sample, we ended up with like 1.3 million different words. At this point, we were trying to just establish a baseline, which is the point at which you can measure everything getting better. So we intentionally wanted something pretty sucky. So we didn't do any fanciness in terms of stop word removal or stemming or other fancy things you've probably heard about. We were trying to get, the worst, suckiest thing we could and go from there. Because we wanted to be scientific about it and be able to measure it and quantify it. Because it was so big, we did say that it would be reasonable to say, look, this word needs to appear on 5 distinct sites, not just documents, but actual top-level sites. And just doing that simple filter reduced a huge amount of garbage and gave us a bag of words that was about 460K, 460,000 words. So the code for it is more or less along these lines, where basically we had an RDD where each line was kind of a JSON map, or it was a map at this point, came from JSON documents. We basically mapped a pair. RDDs have a thing, kind of a key value pair operation, where if you put it in a tuple, it makes it easier to group by and do certain operations more efficiently. So we extracted the site from the URL, and then we extracted the clean words from each document, bunged them into, mapped that to a pair, and then we did a reduce by key, where basically just take all these sets of words per site, and just used the Clojure function union. Then we mapped back to a pair again, where basically given the site and the words, we want to split it out, so words and just a number 1, and then we added those up per word, and then it just had to be 5 or more, basically. So that's a brief example of how we created the bag of words. So random forests is a type of classifier. It's an ensemble of decision trees. Basically means a decision tree, briefly, it looks at features and says, oh, there's a huge number of them that are this or that, so I'll take this as a decision point and split it into 2 buckets. Random forests, they use a statistical method called bootstrapping for selection, and they do this on both the feature set, they subsample from the features that you give it, and the training data that you give it. It's not deep learning, but it's still extremely easy to use, and it's very, very effective. Arthur C. Clarke once said, any sufficiently advanced technology is indistinguishable from magic. For me, random forests are the closest thing to magic going. Even with our crappy, unfiltered bag of words, we were able to get pretty good results with the random forest classifier, an F measure of like 0.86 on that huge, indiscriminate bag of words. Here's a little bit of code. I'm going to have to start speeding through things, but here's a little bit of code for just training it. So as you can see, most of that's just default attributes and creating the model. So there's nothing particularly interesting there. This is how you kind of prepare things. It has a little, in the beginning, we subsample stuff. Then we just make sure we have a labeled point. We split our data into a training set and a test set with a known seed. We cache both of them because we'll be using them multiple times. And then, again, we create the model, like from the last slide. It's pretty straightforward to use. And then topic modeling with LDA. LDA, which is latent Dirichlet allocation. A topic model which infers topics from a text corpus. Basically, it does a bunch of statistical magic and graph theory and stuff to cluster, creates cluster centers around topics where the documents are the rows, that you feed it as input. The features are vectors of word counts, like bag of words repeated. If it's an unsupervised learning technique, but you do need to supply the topic account. Again, from the DMOS data, we had topics for each of our points, so we know roughly how many topics we're going to be using. LDA can be quite touchy to run on large documents. Got a lot of out-of-memory errors on executors, strange errors, as you can see. If you're ever doing this and you ever see from Spark, an error, something about, spark.accadet frame size, do not change this. Just do not change this. We were finally able to get a trained model after reducing our bag of words. We had one bag of words that was 460K. We then did some stop word removal and other things, got that down to about 160K. LDA was still blowing up. Did some other things that, if anyone wants to know, they can ask me later, how to get it down to 11K. We trained this on about 100,000 documents with a roughly even split between our fashion, non-fashion in the corpus. Again, we just trained this LDA model basically for this talk. There's other things we're going to be doing with it. We have a lot more fanciness planned, but if anybody's wondering, well, why did they create an LDA model for that? Part of it was just for this talk, but you could also use it for things like feature extraction or feature dimensionality reduction, or there's a number of different things you can use. I'm going to skip briefly over this. It's here, it'll be in the slides if you want to look at it, because there is a demo. If I can get one, this is always fun, where's the mouse? Oh, there we go. Okay. Oh, no, don't go too far. Sorry about that. Go back. So, if we start with Manning, so we can see, so this is just like 15 or 16 topics from the model we created, and just a few words from each, otherwise the browser kind of goes gaga. But just wanted to show you that even with this, there's some interesting explorations you can do. So this is our WikiLeaks topic that had Manning in it. And then we can see, okay, well, there's international in that as well. And that leads to a topic we've just hand labeled as news. And then from news, there's loads of other topics. And even there, there's lots of interesting things you can dig into and explorations. So if we go to fashion, if we type properly without the demo effect, we can see there were two topics here. One we hand labeled as fashion magazine, which had a bunch of other words, magazine, that also shared our clothing and designers topics, so on and so forth. So what's the point? What did we do? We took pre-scraped, pre-labeled data from DMOS and Common Crawl. We used Clojure and Spark and sparkling bindings to munch the data. We used the MLlib and state-of-the-art machine learning tools to analyze the data and explored it for insights. So what can you do? Interestingly enough, there was very little fashion domain code in what I did there. There was one SQL statement that selected for Ashen because my version of SQLite didn't have iLike, and there was a similar predicate in Clojure. That was the only actual domain-specific code in pretty much everything we did to get that result. Even at this stage, there's a lot of interesting information. So the Manning was Bradley Manning. For those who didn't pick up on it, one of the guys who actually dumped a load of the information on WikiLeaks. There's lots of interesting directions this can go that you guys can take it for your own domains. Some of the things we're planning on doing is we're going to run the classifiers over all the Common Crawl data. So we're really interested in finding pockets of fashion-related information that aren't necessarily linked off the big authorities. You know, maybe some small counterculture, fashion sites, or their own independent subcultures. We're also going to use LDA models to find out, well, what are some of the concepts or topics within fashion itself. Again, these are things you guys could explore in your own domains. There's a lot of cool things you can do and have fun doing it. So thanks for your time. I hope you enjoyed it and found it useful.